We were working with the numbers from 1 to 10, and we found that 3 has an inverse, but 4 does not. And in fact, we also found that 5 does not have an inverse. And we claim that if a number, say a and 10, has GCD 1, then a will have an inverse with respect to 10. And also let me remind you what I mean by an inverse here. We defined a very tricky looking operation in the last video, and it was like this, that we operate a and let's say b in this following manner. We multiply a with b and divide the product with 10. Whatever the remainder is, that is we declare that as the output of this operation. So this is the operation, and that is the set that we are concerned with now. And if this output is 1, that is, if a star b is equal to 1, then we say a is an inverse of b and b is an inverse of a. And we found that there are ways to argue that 4 will not have an inverse or 5 will not have an inverse. And by trial and error, we found that 3 does have an inverse. For example, if we multiply 3 with 5, or rather, if we operate 3 with 7, then the output is 1. Why? Because you would normally multiply 3 with 7, as you would do, to get 21, and then divide that by 10 to get 1, which is the final output of this operation. So 3 is the inverse of 7, and 7 is the inverse of 3. That's the general idea. Now, the question is this: how can we guarantee that a particular number has an inverse? So that's in fact the goal of this discussion, that we want to show if GCD of a and 10 is 1, then a has an inverse. This is a very tricky question, that somehow the GCD of a and 10 is linked with the fact whether a has an inverse or not. So we have to look into it a little bit more carefully. But before we do, as usual, let's look at an example how we can actually compute the inverse. You see, from the previous video, we know that 3's inverse is 7. But what if we did not know that? Is there a way to compute the inverse? Well, let's look at one way to compute the inverse. So 10 is the reference number in this case, because we are looking at numbers from 1 through 10, and we want to find out the inverse of 3 with respect to 10. So what we will do is, we will divide 10 by 3. So 3 times 3 plus 1. So we found this 1 at the very end of this equation. So we can keep it like as it is on the right hand side and bring the rest of it to the left hand side. 3 times 3 is equal to 1. Okay, so let me remind you, what is the meaning of an inverse? If x is the inverse of 3, then we know that 3x when divided by 10 will give the remainder 1. That's the meaning of inverse here, which basically means that 3x minus 1 is equals to some 10 times quotient, because 3x minus 1 will be divisible by 10, and 10 times something will be 3x minus 1. Alright, so which would actually mean that 3x minus 10q is equal to 1. 3x minus 10q is equal to 1. So we want to write an equation like this. If we can, then that x will be our inverse. If we can write an equation like this, then the x will be our inverse. Now, if you look at this previous equation that we found, it is almost like this equation. Why? You say it's 3 times negative 3 minus 10 times negative 1 is equal to 1. So it's almost like this. It's not exactly like this, because it was 10 times 10, so 10 times 1. So to make it look like this, I made this adjustment of signs, but otherwise it almost looks like this. So we are almost there, we're not quite there. So negative 3 could have been our inverse, but again we are restricting only from numbers from 1 to 10. So we cannot have negative 3, that's the problem. So but we can do something else. We can do an adjustment. So this is a trick. What we will do is, we will add 3 times 10 and we will subtract 3 times 10 to the left hand side. So in effect we are adding nothing. So why will that help? Because now we can group this together. So 3 times negative 3 plus 10 minus 10 times 3 minus 1 is equal to 1. Right? So what is this? This is 3 times 7 minus 10 times 2 is equal to 1. So this is the desired equation. You see why? Because if I write it here, 3 times 7 minus 10 times 2 is equal to 1 is precisely, it looks like this equation that we wanted it to look like. 3x minus 10q is equal to 1. 3x minus 10q is equal to 1. So we know that this x would be our desired inverse, so 7 is our inverse of 3 in this particular case. This is sometimes known as the Euclidean algorithm. Whether this algorithm will always work or not, that requires some work of number theory. But it is important that you understand what is Euclidean algorithm. And this is the example to get you started with the Euclidean algorithm. So maybe we can work on another example, and this will right away do the job. So let's take our reference. So let's take the set from 1 to 20. And let's take the number 7 again. And find its inverse with respect to 20. So find the inverse of 7 with respect to 20. Can you do that using the Euclidean algorithm? And it should work because 7 and 20's GCD is 1. So you can pause the video here and try it yourself once. Otherwise, you can keep on watching. Let's write again. Let's divide 20 by 7. So 7 times 2 plus 6 is 20. If you divide 20 by 7, the remainder is 6 and the quotient is 2. Let's divide 7 by 6. So I'm dividing 7 by 6. So 6 times 1 is plus 1. That's where the Euclidean algorithm ceases to work, or rather it stops, the process stops as soon as we reach this 1. Will we always reach 1? Well, my claim is if the GCD is 1, then we will always reach 1 at the end of this process. It requires a proof. But for the moment, let's accept that. And let's isolate this 1. This is 7 minus 6 times 1 equals to 1. And now you can replace this 6 by 20 minus 7 times 2, right? Because you can take this 7 times 2 to the left-hand side. So I'll replace this 6 by this 20 minus 7 times 2. So I'll have 7 minus 20 minus 7 times 2 times 1 is equal to 1. So what do we have? Well, we will have 20 times, 7 times 3 minus 20 times 1 is equal to 1. Okay, so we again have an equation like this, and we know that that's what our aim was, because remember, if x is the inverse of 7, then 7x will give remainder 1 when divided by 20, right? So, or 7x minus 1 would be 20 times some quotient, or 7x minus 20 cube would be 1. Now, this particular equation where we arrived looks awful lot like this one. So, this 3 is our inverse of 7. That's how the Euclidean algorithm works. You can create another example and give it a try yourself. But the real question is, why does the Euclidean algorithm work? Why, if the GCD is 1, this particular step, the last step that we ended up with 1, it will always happen? Therein lies a little bit of interesting number theoretic argument. But for the moment, let's stop out here. Link in the description will take you to more resources and the next video as well. Take care.